This is slide number 67 and I am your presenter Asloob Mudassar. Application of frequency plane filters. So far we have discussed two main frequency plane filters. One was Vanderloo filter, the other was joint transform correlator. And here we are going to discuss the applications of such frequency filters. Most common application of these frequency plane filters are given, which include application of matched filters and optical pattern recognition problems. Problems related to these applications will also be discussed. Matched filters. Assume that an amplitude object O at the zeta eta plane in the transmission mode is placed at the object plane of a coherent processor where it is illuminated by a normally incident plane wave. The coherent processor will produce an image, an amplitude image I, at the image coordinates u and v of the object O, which was placed at the zeta and eta plane at its image plane. That is, the image will form at the image plane, which can be represented by the following equation. So the imaging equation we are writing is I at the coordinates u and v, which are the image plane coordinates, is equal to the double integration over the object O at the zeta and eta plane multiplied by the kappa as with coordinates as a difference of coordinates u minus zeta comma v minus eta, and the integration is with respect to d zeta and d eta as shown in equation number 36. Kappa has been mentioned as a difference coordinate. It means that we are talking about the space invariant system, and kappa is the amplitude impulse response of the coherent processor. Equation number 36 in the symbolic form can be written as given in equation number 37. So the symbolic form of equation number 36 is I is equal to O convolved with kappa. And the Fourier transform of equation number 37 is given by as given in equation number 38. So we have applied the Fourier operator on both sides, and you know that the Fourier of small I is equal to capital I at the frequency coordinates fx, fy, and the Fourier operator will operate on O, giving you capital O at the frequency variables fx, fy, and the convolution sign will be converted into multiplication sign due to the convolution theorem, and the Fourier transform of kappa is equal to capital K at the frequency coordinates fx, fy. So capital K is actually the transfer function of the imaging system, or you can say that it is the spectrum of the point spread function, which is kappa. So kappa over here is the point spread function, and the capital K is the transfer function of the coherent imaging system. So this is the equation, which is the equation in the frequency variables. So that is at the frequency variables we have these connection, that is the intensity spectrum, that which is capital I is related with the object spectrum, which is capital O multiplied by the transfer function capital K of the imaging system. And you know that all these are in the frequency variables fx, fy, as given in equation number 38. So this is the fundamental equation, and you know that if we place the filter as we have referred to, as we have previously called that the frequency filter, frequency plane filter, so it means that the frequency plane filters will be placed over here. So at what position? Let's see. Where capital O at the frequency coordinates fx, fy is the Fourier transform or the Fourier spectrum of the small object O located at the zeta eta plane, and capital K at the frequency plane fx, fy is the system transfer function or the Fourier transform or the Fourier spectrum of the impulse response kappa of the system. In Fourier domain, O star, which is the complex conjugate of capital O at the frequency plane fx, fy, acts as the matched filter. So look very carefully that capital O conjugate of capital O or the conjugate or the complex conjugate of the spectrum of the small object O acts as the matched filter. A frequency plane filter with amplitude and phase transmittance equal to this. So if we have a filter which we call a frequency filter, and if that filter has an amplitude and a transmittance equal to this, which is O star as a function of fx comma fy, is placed at the Fourier plane of the coherent processor as shown in the next diagram, or equivalently we can introduce the following transformation. So you see that the filter is placed over here, that is the transfer function is at the location of the transfer function, that is the transfer function will be replaced by O star, that is a complex conjugate of O at the frequency plane. So let me show you the diagram first. This is the coherent processor for matched filtering. Look at, this is a 5F system. The point source is located in the front focal plane of the lens L1. It means that the L1 will generate the plane waves, and the plane waves will illuminate the object O at the zeta and eta plane. And the lens L2 will generate the Fourier transform of this object at its back focal plane, which is we called the frequency plane or the Fourier transform plane. And the lens L3 will take the inverse Fourier transform of this frequency spectrum and will give you the image at the image coordinates. So at the image we have the UV coordinates, at the object we have zeta eta coordinates, at the frequency plane we have the fx and fy coordinates. So you see that this is the filter, this is the place where we can place our filter. So the matched filter or the frequency filter will be placed over here, and the matched filter in this case is O star, that is a complex conjugate O at the and placed at the frequency plane fx comma fy. So this is our system that is used for the matched filtering. So you see that the matched filter, this is the equation where we have placed the matched filter. So this is the intensity. In equation number 40 I am talking about this. On the left hand side we have the spectrum of the intensity at the frequency coordinates fx comma fy. On the right hand side we have capital O, which is the spectrum of the object O at the frequency plane fx comma fy, because this coherent system will generate, if we have O, it will generate the capital O, that is the spectrum will be generated at the frequency plane. So capital O will be generated at the frequency plane, and you know that we have to place a filter over there. So this O star is actually, that is a complex conjugate of O at the frequency plane, is actually the filter that we are placing. So this filter is placed over here, and you know that I have also labeled that the filter is designated by O star at the frequency plane fx comma fy. So now you look at the right hand side, we have O multiplied by its complex conjugate. It means that the right hand side in equation number 40 can be written as the absolute square of capital O. And you know that the absolute square is a positive quantity, cannot be negative. It means that the left hand side, that is I, that is the spectrum of the image at the fx and fy coordinates, is also a positive quantity, that is non-negative quantity. So Fourier transform of equation number 44 takes the following form. So we are going to evaluate the Fourier transform. Why we are going to evaluate the Fourier transform? Because this lens L3 will take the inverse Fourier transform of the data at the Fourier plane, or that is the data which is incident on the lens L3 after passing through the filter. The lens L3 will generate its inverse Fourier transform, and the image will be constructed at the image plane. So the Fourier transform of equation number 40 takes the following form. Actually, in principle, we are taking the inverse Fourier transform, because in equation number 40 the variables are the frequency variables, and to convert them into the image variables we have to take the inverse Fourier transform. So the inverse Fourier transform of the left hand side, and also we have used the inverse Fourier transform operator on the right hand side. So the inverse Fourier transform of this capital I will be represented by the amplitude image capital U with a subscript img, and at the image coordinates u comma v. And on the right hand side, this inverse operator will operate on the two functions, that is on capital O and will operate on O star, that is the complex conjugate of capital O. And you know that since these two functions are multiplying before we take the inverse Fourier transform, then after the Fourier transform we have to have the convolution between these two quantities, because we have applied the convolution theorem over here. So you know that I have represented the inverse Fourier transform of capital O as a small o at the image plane, that is O as a function at the image coordinates u and v, convolved with the inverse Fourier transform of O star is represented by O conjugate at the coordinates minus u comma minus v. So you see that now this is the convolution between O and O star, and you know that we can represent this in terms of the integral, that is applying the convolution integral on the third step. We are getting the fourth step in the form of an integral as given in equation number 41. So you see that we have a double integral, and we have O as the coordinate zeta and eta, and we have O star with the coordinates zeta minus u comma eta minus v, and the integration is with respect to d zeta and d eta. So you see that we have converted the convolution definition over here as a last step in equation number 41. But look very carefully at equation number 41. The integral in the last step of equation number 41 represents the autocorrelation integral. So this is the autocorrelation between the object O and with its complex conjugate is referred to as the autocorrelation. So actually the integral in the last step of equation 41 is actually the autocorrelation. So it means that the image on the left hand side will give you the autocorrelation signal at the image plane. And you know that when an autocorrelation peak will appear at the image plane. So u with a subscript of imj at the image coordinate u and v will give you a peak at some point where there is an exact correlation between the two signals, that is O and its complex conjugate, where they exactly match with each other. We get a peak over there in the image. In the presence of a frequency filter O star, that is complex conjugate of O at the frequency plane fx, fy. So you see that this is our filter at the Fourier plane. Then if we are placing this filter as the Fourier plane, it means that we are using O star at the variables at the coordinates minus u comma minus v can be regarded as the impulse response of the coherent processor. So you see that if our frequency filter is O star, then small o star at the frequency at the image coordinates minus u and comma minus v can be regarded as the impulse response of the coherent processor. In the same way as we call capital K in equation number 38 as the Fourier transform of kappa, because kappa is the impulse response of the system or the point spread function of the system, and you know that capital K is actually the transfer function. So we have replaced capital A with capital O star. So you see that in this equation, then over here the quantity that will appear will be O star, small o star at the coordinates minus u and minus v. That is this. In the presence of the frequency filter O, capital O star at the frequency plane, then O star, small o star at the image plane minus u comma minus v can be regarded as the impulse response of the coherent processor. The last step of equation 41 shows that the image field u img at the coordinates u and v is the autocorrelation of O at the image coordinates u comma v, and the autocorrelation peak will appear at the image plane. So the simple is that this equation, you know that 41 equation gives you the autocorrelation. So an autocorrelation peak will be detected. So you see that in the coherent processor, if you are placing an input which matches with the frequency plane filter, then you will see that you will get at the image plane a peak over there. So the peak will indicate that the object that you have placed, its spectrum matches with the spectrum of the filter that we have placed over here. So in that case you will get a peak over there. But if the object is different, then you see that we shall get a cross correlation peak. That is, the peak will not be as sharp as in case of the autocorrelation. Now, if the frequency plane filter is O star, that is the complex conjugate of capital O. So this is our filter, and the input is O at the UV coordinates is replaced by a different input, say O2 at the zeta and eta plane. Then the image field, that is U image, will form the cross correlation peak, that is the cross correlation between O and O2. That is O at the UV coordinates and O2 at the zeta and eta coordinates, as obvious from the following equation. That is from equation number 42. So you see that what is the difference between them? In equation number 41 we have O and O conjugate in the object space in the last step of the integral in equation number 41. But you know that now modifying this definition, that is if we are placing this object O is replaced by, that is O at the zeta and eta plane is replaced by O2 at the zeta and eta plane coordinates, then what will happen? The integral above will take the following form as given in equation number 42. So we have O2 at the image plane coordinates U, and we convolved with O star at minus U comma minus V. Then you know that this convolution can be converted into the integral form, which is this as given in equation number 42. And the integrand are O2 at the zeta and eta plane multiplied by O star at the coordinates zeta minus U comma eta minus V. The frequency plane correlation, the frequency plane equation corresponding to equation number 42 or the counterpart of equation number 40 can be written in the following form. So just take the Fourier transform of both sides of equation number 42, especially from the first step of equation number 42. We have I2. I2 is actually the spectrum of the U image. So the amplitude image. So I2 is the spectrum of the amplitude image at the frequency plane, because we have used the frequency variable fx, fy, and on the right hand side we have the spectrum of O2, which is capital O2 at the frequency plane fx, fy, and then we have multiplied with the spectrum of the O conjugate, which is capital O conjugate at the frequency plane fx, fy. So this is equation number 43. So let me compare this equation number 43 with the equation number 40 over here. So you see that in equation number 40 on the right hand side you have capital O multiplied by the complex conjugate of capital O, which means that this the right hand side can be written as the absolute square of capital O, which is a real quantity, that is a non-negative quantity. But you know that here in this equation, that is in equation number 43, we cannot say, because we are multiplying on the right hand side by O, that is the spectrum of O2 multiplied by the frequency filter, which is O complex conjugate. So you see that now the transmission through these one will not be real, because we cannot write the right hand side as the absolute square of any of these quantities. From equation number 40 it follows that I as a frequency at the frequency plane is real, which means that all the frequency plane phase curvatures, and are exactly cancelled out, and the wave fronts propagating away from the frequency plane will be the plane waves. That is reference to this equation 41. You have placed O over here, the spectrum of which one matches with the filter at the frequency plane. Then you know that the field after that one, that is the field passing through beyond this frequency spectrum, will be plane wave, and L3 will focus that plane wave at a single point, giving you the peak, giving you the autocorrelation peak. Okay, however, and you know that the plane wave means that all the phase curvatures are exactly cancelled out at the frequency plane. However, phase curvatures corresponding to I2 at the frequency plane are not cancelled out, as the quantity is not real, because the right hand side is not a real quantity. O conjugate at the frequency plane acts as a frequency plane matched filter when the input has a frequency spectrum equal to O, capital O, at the frequency plane. So you see that if you have placed an input in the coherent processor, and the spectrum generated by that one is capital O, which matches in such a way with which has a frequency spectrum, which has a frequency filter corresponding to O star, that is the complex conjugate of that one is the filter, then you know that under that condition we can say that a matched filter is placed. Whereas in the space domain, O star at minus zeta and minus eta acts as the matched filter for the space domain input O. So you see that if you are placing an input O at the image coordinates, then you know that the same input, at the same object, the input O star at the coordinates minus zeta and minus eta will act as the matched filter in space domain. So O, small o and small o star are the matched filter corresponding to each other, whereas in the frequency domain, O star, capital O star is the matched filter for the spectrum of capital O at the frequency plane. So UIMG, that is the amplitude image at the frequency at the image plane with coordinates u and v, is the coherent amplitude at the image plane given by equation number 41 and 42, and the corresponding intensity is given by the absolute square of this amplitude image. So this is the end of slide number 67.